Okay, if everybody can find a comfy place to sit, we're ready to get started. And again, I'm able to hand over to one of my esteemed colleagues here. I'd like to introduce you to Dr. Peter Phillips. And Peter is at the University of Saskatchewan in the Johnson Shoyama School of Public Policy. He's worked very closely with the Global Institute for Food Security, both in advising us on policy issues and also helping us an awful lot with our overall strategy. So Peter, will invite you onto the stage to host the rest of this session.
Thank you. Thank you very much. It's a pleasure to be here today. The topic is emerging technologies for global food security. There's two parts to that. One is we have to talk about the cutting edge of where technology is, where it might be, and where it's going over the next 5 to 10 to 15 years, which is the window we do much of our planning on. And then we have to talk about the application of technology. So in a way, this conference embodies the two challenges of food security. Scientific knowledge and capacity is a necessary condition. I think that was a conclusion of all the panelists up there yesterday. Nobody was saying science isn't part of the food security solution. But it's only a necessary component. It's not sufficient. Most of the commentators yesterday and the panelists today will talk about what is needed to translate science from a good idea to an application that has technological merit and effect, and get it adapted and adopted and used in the global food system. So science is not sufficient. We need to talk about first where and how we will bring forward new, better, and more diverse technological capacities that will allow us to advance the productive capacity of agriculture. And we need to talk about where and how we can find stronger, more resilient, better coordinated, more responsive regulatory and market systems that will enable those technologies to go from good ideas to best practices and uptake and use and effect and impact in terms of food security. So this panel session addresses those two challenges. We have two speakers today. I'll introduce them in aggregate, then I'll commandeer them up and down the stage. Dr. Neal Gutterson is the Vice President of R&D with DuPont Pioneer, where he leads all of the R&D and development functions across the spectrum. And so it's everything from germplasm to breeding systems to biotechnology-derived solutions to the undiscussed so far, but increasingly important data analytics part of the breeding system. Before joining Pioneer, Neal was engaged in a variety of entrepreneurial startups and firms, including Advanced Genetic Systems, DNA Plant Technologies, and Mendel Biotech. He holds a BSc in chemistry from Yale, a PhD in biochem from UC Berkeley, and was a part of the Stanford Business School on Emerging Companies Executive Program as a postdoctoral training. He's an inventor on more than 30 patents, and he currently sits on the CIMMYT Board of Trustees. I regret to inform you, and I think you all got a little tiny sheet, but if you're like me, you might have had to take your glasses off to read it. Dame Ann Glover is unable to join us today. She sent her regrets late last week. She's had a death in the family and just was unable to attend and join us. So on short notice, we commandeered a colleague and a friend of mine from the University of Saskatchewan, Dr. Stuart Smythe. He's an assistant professor in an industry-funded research chair in agri-food innovation at the University of Saskatchewan in the College of Agriculture and Bioresources. Stuart gave me one bio. I'm going to give you the bio I know as him as a human being and as a colleague and friend. He grew up on a mixed family farm in Saskatchewan, did a degree in political science, and practiced for an extended period of time as a consultant in the agri-food development space. He turned up at my door one time and said he wanted to return to university and do some graduate studies, and by the time we were done, we've spent 20-some years working together. He completed a PhD in an interdisciplinary program on biotech and society. For a period of time, he worked with AgWest Bio as a regulatory advisor and has been a research scientist and now is a tenure-track faculty in the Department of Agriculture and Bioresources Policy, Business, and whatever, AgAc. They have trouble figuring out what their name is sometimes. He's the co-lead with me on the social science component of the large-scale project that GIFs has talked about a number of times already. He's the co-author and editor of an expanding and extensive library of journal articles and books on agri-food innovation, including most recently both a handbook and a research collection on agriculture, biotechnology, and development with Edward Elgar. They're large enough that you could use one on each side as a weight lift, an exercise machine. So today we have the two speakers. They're bookending the debate. At one level, the cutting edge of where people think technology may be coming, and I haven't received my Economist yet this week, but people tell me the current issue of The Economist is full of stories about agriculture, and CRISPR-Cas is one of the technologies that people are focusing on as cutting edge. And at the other end of the spectrum, we'll listen to Stuart talk about the regulatory regimes. So with that, let me invite Neal to join the podium.
Thanks very much. And thanks very much for the introduction, and to Morris for the invitation to come and share with you some of what we're doing at DuPont Pioneer and DuPont more broadly. What I want to do then is actually spend the first maybe third or so of my remarks about food security broadly and what we're doing to understand the issues of food security and the support that we have for the Economist Intelligence Unit in delivering the Global Food Security Index on an annual basis. So I'll talk a bit about some of the learnings that come out of the work we've done with The Economist on that. And then I want to talk about some of the work we're doing in, as was mentioned, CRISPR-Cas advanced breeding as a way to bring more quickly some really important innovations that we think have a real strong potential to impact the developing world. And of course, that will depend upon the uptake of the technology, but it's a technology, this sort of novel ways to breed through genome editing that we think can be broadly used in a wide range of crops. And I want to give you an introduction to what we're starting to do and where we think we can go with that technology. So with that in mind, so I think everyone knows who DuPont Pioneer is. We work globally. We are the world's leading developer and supplier of advanced plant genetics. And we also are very strongly committed to providing services to our customers for the 90 years that we've been in business. And so genetics is a key piece from Pioneer. In the DuPont landscape, our crop protection colleagues also deliver crop protection solutions to help our customers get to the maximum productivity and profitability from their farms. And as was mentioned also, we are more and more bringing data behind the services we deliver to growers to help them better understand what to plant on their fields, when to plant it, and how to manage it. And we think the opportunity in data is a really big one. So we're involved in innovation, science-driven innovation company for the long term. And we believe that mix of technologies is really critical to helping to feed the world, both in the developing world and in the mission that we're talking about here today, the developed world and the developing world. Certainly, there's a lot of science that's needed to feed the world. We work in creating what you might think of as global assets, our germplasm, our traits, the chemical crop protection products that we develop. But we know absolutely that the solutions are local, and how we bring together those products in packages that can enable growers to have not just solutions to challenges from pests and pathogens, but durable solutions to those challenges is part of what we focus on. We know collaboration is critical. We collaborate very broadly. I'll touch upon that theme a bit again when we talk about genome editing and CRISPR-Cas advanced breeding. We know that science must be adopted locally and used locally and interact with what is understood at the local level, and that our solutions must be sustainable, not just because they're durable products, but also because they help farmers do a better job in producing with fewer inputs. And that is a key part of our mission as well. So what are some of the food security issues? And this is a topic, I don't have to dwell on it, but just to remind you, We all know that the challenges of population growth, climate change, impacts on soil globally, the yield challenges we have with breeding. And key to that, as I said a moment ago, are collaborations. And certainly across all the technologies we deploy, we work very closely with farmers, continually with civil society, with government, with NGOs. And again, I'll touch on that a little bit more when I get to the end of the discussion about advanced breeding through CRISPR-Cas. And of course, innovations are critical. And getting innovations deployed, the theme here, from where I've sat in the CIMMYT board for the last 3 years, is really not just about technology, but about innovations in infrastructure and in seed production systems. We know that complex technology is difficult to adopt, and technology needs to be fairly simple to be taken up broadly, especially in the developing world where there's usually less infrastructure to support that technology. So what are our food security goals? We announced, I think it was about 4 years ago now, that by the end of 2020, we would help the world meet the challenge of achieving global food security in 3 important ways. One is investing into innovation to feed the world, and I'll touch on that in a moment. The second is engaging and educating youth, both understanding the technologies that are important to the future and bringing the youth into the mission of feeding the world is part of what we're focusing on. And then lastly, it's critical if we're going to be successful that we don't just deliver products to the developed world customers, but to customers in the developing world, very different sort of customer base, not thousands of acres, but single digits of acres in many cases. And so focusing on smallholder livelihoods, on rural communities is part of what we do by engaging with, in our own markets in some regions in India and Africa, but also with partners through NGOs and international ag organizations. So where are we on that path to supporting food security? So the top 2 pie charts show our progress in the first 3 years on innovation investment. Our commitment was to invest $10 billion in R&D. And you can see we're on track to deliver against that goal. We've already invested nearly $4 billion of that $10 billion in the first 3 years towards our commitment. Ultimately, it's not about what you invest, it's about what the outcomes are, and it's about the products that we're developing. We had a commitment to deliver a certain number of products, 4,000 products, and we're well ahead of pace to deliver those products into the market to support this mission. Come to the bottom on the left side. Youth engagement is an important principle for us, and we've worked very broadly with communities in that way. We've worked with, for example, in the Ukraine with ag students, focusing on some of the challenges in those local regions. And we've also reached down to lower levels, and we've worked with 3rd and 4th grade students in Brazil, looking at sustainability of agricultural systems. So we're deeply engaged in those processes, and you can see that we already exceeded that 2 million target of engaging youth, but we will continue to do that sort of work. And then the last point, in terms of smallholders and rural development, we have a target of impacting the livelihoods of 3 million smallholder farmers. We've achieved about, about a fifth of that so far. So there's a ways to go on delivering that. The number of ways we do that, and one example is work we do in India. We've established a rice farm, for example, to reach out to smallholder growers in the province of Uttar Pradesh. So let me now talk a little bit about work we do, as I mentioned, partnering with the Economist to deliver a global food security index. And we do this annually. The 2016 edition of the index just was published last Thursday. So I encourage you to go to the website you can see on the slide to check that out. There's an entire Excel spreadsheet of data behind it, and then there's a nice report that is delivered. We think this is a unique set of information. Clearly, if we're going to impact the mission, we have to measure where we are and where we're going. If you don't measure an outcome, you can't really improve it. And so there's quarterly adjustments made to that index. We release it on an annual basis, and there are some unique quality indicators in there to help us really understand, country by country, some of the issues that underlie challenges of food security. And so what we're really after are, what are some of the root causes that limit progress against food security? And so we do there's 113 countries in that food security index, and we hope that by providing understanding to those countries, that in some cases, countries can perhaps lift themselves up by better understanding what the challenges are and what other countries are doing to improve global food security or food security in that region. So what have we learned? Five key trends are highlighted here. The first is that most progress, or the best progress, is made in upper middle income countries. The next level would be in some of the lower middle income countries. Obviously, as you go down that income level, the challenges get steeper. What we have seen, though, is that the average share of household spending against food across countries in the index has dropped by 11% in this 4-year period, and that's a key part of progress. We know that the developing world spends a much higher percentage against food to deliver their local food security than the developed world does in general. We also know that we've learned that the challenge of elevating food security locally is really impacted by the rapid urbanization that's going on around the world. And so we can begin to then look at those issues and look at how we can overcome some of those challenges driven by urbanization that's happening around the world. The fourth point is that while almost 70% of the countries in the index have identified and developed nutritional standards, that means that over 30% still have not developed simple nutritional standards and then applied that through school systems that would help them lift food security in their regions. And so we hope, again, the last point is that this kind of information provides a valuable insight to developing countries, that they can learn from the diversity of solutions in other regions and deliver more diversity in diets and improve food security in their regions. So finally, in terms of what we've learned, there's a number of points to be made on this slide. This is the overall score, and you can see the index on the left. The overall score across countries around the world. And no surprises here where food security is challenged the most. You can see across much of Africa, in parts of Asia, and parts of Latin America. But overall, we have seen improvement in overall global food security. In 2015 to 16, there have been some declines in terms of use of standards for food security that we've seen. We also know that food security is improved when solutions are simple. And I mentioned that earlier. We've learned, obviously, I think many of us, that complex solutions are difficult to adopt. And so even simple solutions like improved storage post-harvest, improved transport infrastructure make an enormous impact on local food security. And that brings me then to some of the things that we're doing, because if we're going to make an impact, it has to be through relatively simple solutions. And as I'll come to, CRISPR Cas Advanced breeding delivers options for growers around the world, for farmers around the world, that are very simple, we believe, to adopt. So this picture just is to introduce sort of some of the technology history behind a company like DuPont Pioneer. You know, our foundation is in the first revolution of crop improvement in the 20th century, which was the development of hybrid systems as applied to corn. And the yield had been pretty much stable in the United States until hybrid systems were really improved. And over the last 60, 70 years, the last 90 years, we have continually seen better gains in yield for our customers through hybrid systems that we continue to deploy in a wider range of crops. So not just corn, but in rice, in canola, and in other crops. Obviously, ag biotech was another important revolution. We bring ag biotech traits to the market, and that's part of the foundation of crop improvement for the future, along with hybrid systems. And now we've recognized that there's a new opportunity that we believe in very strongly, has a potential to be a similar revolution to what we saw from ag biotech and hybridization. And so we have begun to invest significantly in the technology, in the IP that's necessary to practice the technology. And we've gotten here because we've spent the last 90 years investing in the understanding of the genomes of the crops we work in, and without that deep understanding and the sequence knowledge about the genomes we work on, we can't apply CRISPR-Cas very effectively. We've also invested significantly in the ability to transform crops, to introduce molecules into plants and to modify the genomes of those plants. And that combination of CRISPR-Cas, of genomic understanding, and the ability to deliver molecules into a plant cell, that set of 3 tools are critical to our ability to deliver CRISPR-Cas advanced breeding on top of the platform of conventional breeding systems. So many of you may be familiar with this, but I just wanted to spend a couple of slides at least introducing what we mean by CRISPR-Cas and what it is and what it can do. So CRISPR-Cas is a system that was derived from microbes to enable them for an adaptive immunity system to virus infection. But we've taken a nuclease, the Cas9 nuclease, from that system and deployed it in a way that can enable us to edit any genome. And so this nuclease actually can cut, there's 2 nuclease domains, can cut in double-stranded fashion, can cut double-stranded DNA in a clean fashion. And the way that process works is that the nuclease is guided to a particular target in the genome by a very simple guide RNA. Earlier tools for genome editing all required the editing of a nuclease in order to be effective. And that protein engineering was a relatively slow, cumbersome, expensive process. But if all you have to do is synthesize a new RNA molecule to target the genome by just binding to an existing nuclease, that dramatically changes the challenge of targeting any location in the genome. And so CRISPR-Cas has really changed the interest level and the ability of many industries to impact genomes of organisms that are important to them. So once the nuclease cuts, then the cell tries to repair that cut, and that can lead to small mutations. But if we actually use templates, we can actually repair the DNA in a way that we can design the changes we make. And so one of the things we can do with CRISPR-Cas is to create a deletion, either by making a single cut or potentially, and I'll talk about this in a moment with the example I'll give you, making 2 cuts near each other, and by design, deleting a particularly targeted piece of DNA to create a desired outcome. So deletion is a very simple thing to do, just relies on the cell healing those breaks. But we can also either edit or move sequences, and that's driven by a template. So after we cut the DNA, we introduce a template, and that template can have a small change in it, maybe just a couple of base pairs, that enables a minor change in the protein that's produced. For example, maybe taking a resistance gene and making it that maybe has lost the ability to provide resistance to a crop and making it resistant again. Or the idea of moving a gene within the genome. And so one of the important principles here is that we are working entirely within the genome of and the gene pool of a given crop of interest. And so the example here, for example, might be that we take a disease resistance gene from one variety of corn or wheat and move it into another variety of corn or wheat, into its normal location. Something we can actually achieve through breeding, but we can do it much faster potentially with this technology. So I've talked to you about this technology, CRISPR-Cas advanced breeding, and we see it as evidently a breeding technology. It's part of our integrated breeding systems that we're developing and we continue to develop. And there are 3 examples here that highlights why we see it that way. And the point is that the changes that happen through evolution naturally and the changes that we get in our variety development processes through breeding are the same sorts of changes that we can deliver working within the crop system with CRISPR-Cas technology. So on the left, you can see an example in tomato from 2008, where we came to understand that a gene duplication was behind a change in expression that led to elongated fruit in tomato. Just one example of a very simple sort of change that we could do with CRISPR-Cas happens in nature. If you look at the level of our knowledge about the maize genome, which has exploded over the last 5 to 10 years, if you just look at 2 well-known varieties, B73 and Missouri 17, and compare them, there are hundreds of copy number variants. There are thousands of presence-absence variants, places in the genome where in one variety the gene doesn't exist, in another variety it does exist. And you can see exactly where that gene would be in the other variety. And many, many indels, insertions or deletions, and small nucleotide changes, SNPs. We also know that every time we grow plants in the field that a certain number of SNPs, again, single nucleotide polymorphisms, are introduced per generation. So small single base pair changes happen all the time. We use them in breeding. And so again, whether we're inserting a gene from one variety to another, which happens in nature, this is all within the province of the types of changes we can deliver through breeding. So to drive that point home, why is it important that we have a technology that helps us not just deliver specific traits, but actually improve our breeding systems? So all the time, we have elite germplasm that we're adapting to local regions. We have global systems, but local adaptation. And so this example shows one in which we have an elite variety on the bottom left. It's got great agronomics for that region, but it's not tolerant to a particular stress that we care about. And so we may have a variety, and this is often the case, that's got really good resistance to that stress, but is very poorly adapted for that region. And so it normally would take us many cycles of back crossing, as you can see here, to get to a point where the amount of the original source of that resistance gene is so low that it doesn't impact the product we want to deliver, which is the elite variety. And here it shows 3% is left. Well, you can go a couple more cycles and get that down to less than 1%. But even that percentage has some baggage and can actually impact the performance of that variety. In contrast, what we can do with CRISPR-Cas, if we isolate the gene that delivers that stress, is in one step simply move that gene from the one variety into the variety with good agronomics, with elite performance. And so rather than many cycles, we can bring that down to just 1 or 2 cycles. Now we can move corn cycles pretty quickly. But if you think about this in the context that we are looking at many, many different traits we want to combine, if we've got 2 or 3 desired changes we want to bring in at one time, say resistance to a viral disease in Africa requires 2 or 3 genes, then the process to deliver that through CRISPR-Cas is tremendously shorter than the process to deliver that through conventional breeding. And so we think this has a phenomenal opportunity to impact not just what we do serving our customers, but with what all ag organizations do globally who serve their customers through breeding and release varieties through, say, national organizations. So, as I said, we think this is very broadly applicable. On the left, you can see that we're working on this in a wide range of crops today. Every crop on this list is a crop that we either are shortly going to work on or are already doing work in our labs. I'll give you an example about corn and what we're starting to do to bring the technology to the market. But we see it impacting all those traits on the upper right. So yield, disease resistance, drought tolerance are really important opportunities. We can increase nutritional value working within the genome of a crop. And for example, in a crop like soybean, we can improve the oil quality or the oil level or maybe the protein composition in a way that opens up some new market opportunities. And of course, we're using it already to improve our hybrid systems. And we see, as you can see here, that we're committed to bringing our first products, our first DuPont Pioneer branded products to the market in as early as 5 years. And I want to tell you that story because while the first product we're working on is not going to be an economic blockbuster for us, it's an important first step in bringing technology, working with the supply chain, working with our customers, helping them understand the technology in a very measured fashion. So our first product is going to be what we're calling the next generation Waxy Corn. We basically looked at the different options we had, and this is one that we felt had many advantages as a first product. So first of all, it's a very familiar trait to the market. Waxy corn's been on the market excuse me, for many years. It's one we can generate through deletion technology. And so it's a way for us not only to get a first product introduced and understood, but also to perhaps get some understanding of how regulatory agencies and the public might look at this particular class of application of a deletion of a gene, right? No novel protein sequence at all. So the gene is also well understood. If you're going to use this technology, you need to know the exact gene you're going to target and what might happen when you delete that gene. And we know the trait we deliver, and we know exactly how to work with that gene. There are many variants known in nature already. And the product is already identity preserved in the market. And so we can go at a relatively small market, deliver a new and improved version of Waxy, and give our customers choice, in fact. Right? They can use the conventional one or try the new and improved Waxy variety. And ultimately, the reason to do this is that the current varieties we deliver don't have the yield that we would want, and because of the time lag in bringing that trait into our elite varieties, genetics I showed you a moment ago, our products are not as high yielding as we'd like with this particular technology, with Waxy. So what is Waxy corn? It's a pretty simple concept. The Waxy gene is involved in the branching of amylose to amylopectin. And so what we end up with is, instead of conventional corn, where you have 3/4 amylopectin, the branch form, we end up with over 97% of branch chain starch molecules. And so you can see on the right the appearance of Waxy corn, where its name came from. The product, as I'll show you, has a number of uses, and again, very specific uses in the market. So Waxy corn starch, it has food industry uses. As you can see across the top, it's used in dough making, for example, as you can see on the far right. It also has industrial uses. And so it's a very common, impacts binding qualities and sometimes paper quality ultimately, as you can see in some of the pictures on the right there. And it has applications also in textile, in corrugated materials, and other adhesives. So it's broadly used in the market, a very specialty corn product, and it's identity preserved, and we can give customers an option and a chance to understand the technology as we bring it to the market. So what is this new and improved Waxy going to look like? First of all, the current Waxy product is derived from a 100-year-old corn variety when these Waxy variants were first studied. That current product has a non-functional Waxy gene. And as I mentioned before, the challenges include the fact that there's some yield penalty compared to our elite genetics in the products we bring to the market. And it also lags our elite genetics by 2 to 3 years at least. We know that in that variety, part of the Waxy gene is missing. The gene is non-functional. So the next generation Waxy product, using that model I introduced earlier, was instead of doing this back crossing, we go directly into one of our elite inbreds in the hybrid combination. Actually, we go into multiple inbreds because it's a recessive, and you have to engineer both of the parents of a hybrid. So this is actually facilitated as well by this direct transformation process, this direct process of modifying with CRISPR Cas. And we can delete out the entire gene, which is what we've done. And we've brought this in the United States to the USDA. We have a letter from them in terms of how they're going to treat the technology. And now we're working around the world to help regulators understand this first product that we're bringing forward with an entire Waxy gene missing. The properties, other than the yield benefit for our customers, are identical to the conventional Waxy product. So we know that any technology, any new technology, needs to be understood by the public if it's going to be adopted well. And so we believe really strongly in working across a number of groups that are important to understanding the technology and to public acceptance of the technology. It's not just about the regulatory paradigm that we're going to find around the world. The easiest regulatory paradigm is not very useful if the public is resistant to the technology for whatever reason. And so you can see here a number of efforts that we're involved in. So we're at scientific meetings like this to talk about the technology, its value, and its safety. We're working with academics in a wide range of institutions already who we're talking about opportunities to collaborate and partner. We're working with regulators around the world to help them understand broadly the technology, but in general, they want to see an example. And so Waxy is our first product, but there are others we're talking about with them. We're talking to the media. We're working with commodity groups as we began the process of developing the Waxy variety and bringing to the USDA that product that we want to bring forward and getting their opinion on it. We had conversations with the value chain, the millers who will use the technology, to make sure they understand the technology, what it's going to do for their customers, and just developing that relationship with them as we go forward. We're working with international NGOs. On a consistent and regular basis, we're talking to international ag organizations within the CG system. So working with all the voices that we think are important and listening to people. Our first mission is really to understand much more than it is to be understood about what we're doing, and understand their concerns, their issues, how they think about this technology, how they think about any technology that might be new, and how it impacts their thinking about food. We've learned that Food is not like a cell phone, and people's reaction to technology and food is not the same as it is when they get their new edition of iPhone or Galaxy, to be fair to all parties there. So, just to bring this to a close then, this slide really is a reminder of the work that we're doing in helping to deliver some solutions to the developing world. We have a number of collaborations with CG centers, formal and informal. This is an example for biofortified sorghum through transgenics in Africa, a wonderful product that increases vitamin C and other micronutrients. But the points here are, and to summarize, are really clear. Food security is a global challenge. We all understand that. We have to address it at a local level. We have to understand through something like our Food Security Index what the issues really are at the local level. And those challenges are very much part of the mission that we feel at DuPont Pioneer. We know that we have a mission with our stakeholders, our customers, but we recognize when we bring technology forward that can impact the developing world, that we have another mission to help do that. And to do that, that second point really is that collaboration is the key. And especially with new technologies like this, we are looking actively to collaborate with all the sorts of groups I mentioned on the prior slide. International ag organizations, academics, small companies that might want to begin to use the technology to create products for the market. And perhaps lastly, we really do believe that simpler technology is easier to bring to the market and easier to bring to the developing world. The products we develop through CRISPR Cas advanced breeding are going to look and feel exactly like what farmers around the world are used to getting through breeding. And so whether CIMMYT delivers a future product that's got resistance to important pathogens in wheat, or IRRI does the same in rice, to accelerate their breeding and deliver for those customers, this solution is a simple solution that we believe can be adopted in all the important crops. And of course, in some crops, it's even more valuable than others. When you have a complex crop like wheat, for example, a hexaploid, to do the breeding or engineering is even more complicated. And this technology will help accelerate that process, but still deliver a very simple solution, a simple outcome to customers. So we're looking to facilitate the adoption of the technology by colleagues around the world, helping them with whatever expertise that we're developing, and maybe even designing some of the projects that I think will be beneficial, and we're engaged in those kinds of conversations today. So that's the story, that's what we're doing. That's why we think CRISPR Cas advanced breeding is part of the solution for global food security, as well as an important tool for our business. So thanks for your attention, and happy to take a few questions.
Thank you. Very wonderful talk. I want to ask, is the off-targeting effect of the CRISPR is a problem or not?
So the question about off-targeting. So we know that when you target when you target a location, right, if the sequence somewhere else is similar, you could actually end up with making a change in that other location. 2 points I'd make about that. The first is that we are improving the specificity and working on that side of the story as we go forward. And we ultimately think that's going to be a pretty minor issue, to be honest. Of course, we can also know where those locations might be and verify that changes haven't occurred as well. So I think while that is an issue, to be thought about, and we take that very seriously, that in the long term, the technology will be sufficient to deliver absolutely precise changes without off-target changes.
So, Neal, my question was about the IP. So, here.
Oh, sorry.
Right here.
Yep.
Yeah.
Sorry.
My question is about the IP because having just followed this in the popular press, there seems to be competing groups, for the technology, and yet you're obviously making a major investment, so you must feel like you have freedom to operate. So, what's the current IP situation in relation to this technology?
It's complicated. That's the situation. So, I'm not going to talk too much about the actual pieces, but you're right. This is a complex technology, and interference has been declared in the U.S. for 2 of those, the patents coming out of UC Berkeley and the Broad Institute. We're working to create for ourselves freedom to operate, and there's a lot of uncertainty. But we also know that you know, the core technology, right, about CRISPR-Cas, I mean, there's many ways to get there. And I suspect there's not going to be just one simple, you know, dominant position. There may be other sprouts that come up that offer alternatives, or as we improve technologies, that there may be a sort of really critical tool that becomes, you know, sort of a linchpin in sort of the process. So there's uncertainty. We recognize that, but we think we can get there, and that the value justifies the risk we currently face, right? Which is, you know, is true.
Hi. So for the last 20 years or so, agrobacterium has been the major workhorse for genetic engineering. Does CRISPR-Cas have the potential to actually completely replace that? Because you did mention about being able to make 2 edits and replace the sequence with a template. If you can shuttle in any desired gene into that location, isn't that better than the more sort of accidental nature of agrobacterium?
Right. So I think the point is that if you could target a location rather than random delivery through agrobacterium or other means, that has advantages. So, you know, CRISPR-Cas is a tool, and mostly what we talked about today was our application for advanced breeding. But you're right, it is also a tool that can be used to improve transgenesis. And I think there are advantages to that. We are working with that technology as well and designing, you know, landing pads in the genome, which we can verify as to, you know, what impact you have when you put a gene there. So I think there will be advantages to that in the long term. I think there's no doubt about that.
Yeah, there's been some people have raised that some of those groups that oppose GMO technology might equally oppose CRISPR and other new breeding technologies. Have you got any sense of, notwithstanding it may not make scientific or common sense, but have you got any sense of how that might unfold, the same kind of brouhaha that we had over the GMOs? Yeah,
I mean, you know, there are groups in the business of opposing technology, right? So I'm sure they'll be opposing, and we've seen things, right? So you know, there's letters in the you know, published about the technology from groups in Europe and elsewhere. We're trying to learn from, you know, what happened in the last sort of biotech enabled revolution, you know, ag biotech. And I think one of the lessons is talk, be transparent, understand people. And I think, you know, we're really trying to get out very much ahead of that conversation. And I think part of it is that this is a technology that can be broadly used, right? This isn't just something that we want to bring forward and penetrate the market with. I think we're going to see lots of people use the technology. I think that may change the discussion. But, you know, there's certainly risk of, you know, the dialogue going in a way that might not be productive.
Final question over there.
So could you comment on the logic or the decision-making process that you used for pursuing a complete delete of the Waxy gene as opposed to a SNP-based gene inactivation?
I probably could. Maybe we can discuss it a little more offline. I mean, you know, I think the simple story is that if you know, there's some sensitivity perhaps to, you know, if you make a mutation, what happens to the protein? Does it get degraded? Is it a different protein? You get away from all those issues if you just do a deletion. Of course, Waxy itself, the normal variant, is, you know, it's a small deletion itself. And so we just felt that was a much more straightforward way to deliver a product. But,
so do you think it's easier to get through the regulatory system by doing complete versus a SNP-based inactivation?
I don't want to get too much into the minds of the regulatory agencies, and maybe we can discuss that offline a bit. Okay.
On that note,
All right.
I'd like to thank Neal for his talk. And